Yep, welcome back. Today we are going to talk about the derivatives of some important functions. In fact, we call these functions transcendental functions. We don't have to really get into why that is. Some people say because they transcend algebra. They're more than just algebraic functions, in particular polynomials. Regardless, we want to give you the formulas for how to take the derivative. So here we go. Here they are in nice bright colors for you, right? The first one turns out says the derivative of sine x is cosine x, right? So that's pretty interesting that the slope producing machine for the graph of sine x is actually the function cosine x. We'll see that in a second. The derivative of cosine x is actually negative sine x. It would be great if it was just sine x, but it's negative sine x. And you're actually going to learn a little memorization trick later on that basically says if you take the derivative of a trig function that begins with the letter C, it will always start with a negative. That's why I put that in red. All right. And then we kind of go off the beaten path and we talk about the derivative of the exponential function e to the x, right? It's an exponential function with the base of e. Well, it turns out that that derivative is just e to the x. And if you remember when we were doing those numerical estimations, we actually saw that, right? So that's the easiest one in America to memorize, right? The derivative of e to the x is just itself. So what does that mean? It means a slope producing machine on this graph can actually, the slopes can be obtained by just looking at the y values, right? So that's pretty neat. And then the last one we're going to look at is the natural logarithm of x, otherwise known as log x base e. And it turns out that that derivative formula is just 1 over x. You need to memorize those. Now, I am not going to derive each one of these proofs for you. I know that's going to be difficult for me. I'm not going to sleep very well, but I will at least give you the first one, right? Because we kind of have to know where these things come from. So it says, let's prove the first one. And before we do that, we're going to need some information. If you remember that limit we did, limit of sine x over x as x went to 0, that's 1. Well, that's the same thing as the limit of sine h over h as h goes to 0. That was 1. Remember, we proved that with the squeeze theorem. We're going to need that in what we're about to do. And then we're also going to need this limit, the limit of 1 minus cosine h over h as h goes to 0. That's going to be 0. And if you remember, it was the same as the limit of cosine h minus 1 over h as h goes to 0. The way we did that guy, we actually multiplied by the conjugate of the numerator over itself and simplified that way. And we ended up seeing actually this limit embedded in that limit. And then some pre-calculus things that you learned way back when. We're not going to need this guy. You would need this for the other proof I'm going to discuss. But we will need this, that the sign of a sum, right, can be expanded this way. So the sign of a plus b is sine a cosine b plus cosine a sine b. That is just a formula that you learned in your Algebra 2 days, hopefully. All right, don't think you can distribute the sin, right? This isn't sin times a plus b. This is function notation. This is sine of a plus b, and this is what it's equivalent to. So here we go. So if I want to take the derivative of sine x and show that it equals cosine x, what do I have to do? Now, I don't need to do this, but maybe just to give you some comfortable references. We're basically saying, hey, if you know that f of x equals sine x, get the derivative. Well, if you didn't know it was cosine x, you don't have a choice for where to start. And that spot to start is always the definition of the derivative. So I'll write it out, and you should be getting tired of seeing this. The limit as h goes to 0 of f of x plus h minus f of x all over h, right? That is the definition of the derivative. That'll get you the slope producing machine on the graph of f at any point x, otherwise known as the instantaneous rate of change producing machine on the graph of f at any point x. So let's do it. So you're like, all right, well, in this particular problem, my function is sine x, right? So I want to go ahead and do f of x plus h. I put x plus h in the function f wherever I see an x. Well, I see an x right there. So that would give me sine of x plus h, right? Then I have minus f of x. Well, that's just sine x minus sine x. And then all over h. And then limit as h goes to 0 because I've not taken the limit yet. Again, guys, this isn't sin times x plus h. You don't distribute the sin, right? If you should chuckle when I say that, right? So you're like, what do I do? Well, all right, you should put 0 in for h first. And of course, we know what's going to happen. If you do that, sine x minus sine x is 0. The bottom is 0. You get 0 over 0. You get an indeterminate form. So you have to try something. So the thing to try here would be, if only I knew a way to expand the sign of a sum that would be pretty helpful because then I can expand sine of x plus h. Well, lucky for you, I recalled for you the sign of a plus b, only it's not a and b now, it's x and h, but it's done the same way. So this can get expanded into sine x times cosine h plus sine follows sine in that expansion. That's how I remember it at least. Plus cosine x times the sine of h. So that's how this would get expanded. And then the rest of the stuff is minus sine x and then all over h. And we're not out of the woods yet because now we got to do some algebra manipulations that you got to be comfortable with. All right, so the first one is this. I'll notice that this first term in the numerator and this last term, they both have a factor of sine x. So I'm going to pull that out. And you're like, why? They don't all have it, right? So typically when you're solving equations equal to 0, if everyone doesn't have the factor, then yeah, you usually don't want to pull it out. But no one's solving any equation equal to 0 here. So I'm allowed to pull this out of these first two terms. So what do I mean? Well, if I factor out a sine x from just the first and the third, I'm going to get cosine h minus 1. And then I can't forget this part now, plus cosine x sine h, right? That I didn't pull anything out of. Now, again, you're like, well, why can you do that? Well, just think about it. Distribute this sine x, right? Are you not going to get exactly this? It'll be in a different order, but addition's commutative. So that should make sense that you can do that. And so you're like, well, what do you do now? Well, now this becomes those weird limit problems where we wanted to kind of see the limit of sine h over h as h goes to 0 embedded in the problem. You kind of see it right here, right? But this numerator is a plus, it's a sum. I kind of want to break that up. So I'm going to actually rewrite this quotient in the following way. Sine x times cosine h minus 1 all over h, right, plus cosine x sine h all over h. So I basically broke the numerator up over addition, or I decomposed that fraction, or I undid adding fractions, however you want to think about it. Now, you might be freaking out and be like, well, wait a minute, shouldn't that be h squared? And the answer is emphatically no, right? You're adding fractions here. So think about it. If I was to add these fractions, I'm allowed to add them because they have the same denominator. And when you add fractions, you don't add the denominator, you keep it and you add the tops. So all I did was decompose this fraction, right? I use my adding fraction rules in reverse. Sometimes we call this giving out the lemonade, or sometimes we say just decomposing the fraction. So now what do I have? Well, within these guys, and I'm going to take my time here, I have kind of like a product here with some of those limits that I wanted us to use up top, right? So I see this limit embedded in the problem right there, and I see this limit. So just to kind of like drive that home, I'll take my time. I'm going to rewrite what I have here. So now I have the limit as h goes to 0 of, I'm going to have sine x times cosine h minus 1 over h, right? And then plus, I'm going to have cosine x times sine h over h. And you're like, wait a minute, that's not what you did before. How come you're not putting in h over the sine x? That's kind of like what you did before. Well, I'm now breaking up over multiplication, so it's a whole new ball game, right? If I was to put sine x over h, then that would have meant that this would have been a what? In h squared, because when you multiply fractions, you multiply across the top and the bottom. So I'm not putting this over anything. I mean, if you want to, for kicks and giggles, put this over 1, you can. You should all agree that if I multiply across here and here, I will get that. Okay? Maybe I should put the parentheses around here, but I'm not gonna. So now, guys, think about what I have here. Now let's go to limit world. First thing I have is a limit of a sum. And what do you know about the limit of a sum? And oh, by the way, this is the first part of my sum because this is the plus sign. And this is the second part of my sum. The limit of a sum is the what? Sum of the limits. Awesome. Okay. What else do you have now? Well, within each part of those sums, you have the limit of a what? Of a product. And what do you know about the limit of a product? It's the product of the limits. So I could, in one shot, I'm not going to do that in two separate steps, although maybe for no flavor it would be good to. I'm not gonna. I could, in one shot, apply my limit properties and write this as the limit as h goes to 0 of sine x times the limit of cosine h minus 1 over h. as h goes to 0 plus the limit of cosine x over 1 as h goes to 0 times the limit of sine h over h as h goes to 0. Now, why did I want to do any of this stuff? Well, because now I have some recognition going on. I know what this limit is right here. We proved it with the squeeze theorem weeks ago. This limit is equal to 1. I also know what this limit is equal to. Using this result over here and using the conjugate and using some algebra, we showed this limit was 0. And then at one point we said, hey guys, just memorize that, right? This limit is 0. This limit is 1. That's horrible to remember it that way, but whatever. Okay, so now what do you have going on? Well, let's see. So now I have f prime of x equals, well, what's the limit of sine x as h goes to 0? That seems a little weird, right? The limit of sine x as h is varying to 0. Well, there's no h term in here. So this isn't getting affected as h is varying. So it's almost like you treat it like a constant. So the limit of sine x as h goes to 0 is just, in fact, sine x. This is 0, so sine x times 0, that's going to be 0. Over here, the limit of cosine x as h goes to 0, again, there's no h in this, so it's not varying with h. So that's just going to be cosine x. And then times, this limit is 1, and you're like, wowza, look at that. You have that f prime of x is equal to cosine x. So in other words, if I want a command notation, the derivative of sine x with respect to x is actually just the cosine function. So we just proved it. And again, if you're going to prove any derivative formula, you always have to go back to some version of the definition of the derivative. And that's what we did here. All right, so now at least I can sleep at night knowing that I showed you that one. At the end of the day, guys, you just have to memorize this. The derivative of sine x is cosine x. And on top of that, and I'm not going to prove these others for you today, but you got to remember to memorize that the derivative of cosine x is negative sine x. The derivative of e to the x is going to be e to the x, easiest one in America. And the derivative of ln of x is 1 over x. So that's the stuff that you have to memorize. All right, so that being said, let's do a couple of things. First off, isn't it kind of interesting that the derivative of sine x is cosine x? So I created a little Desmos here, which I actually like. It wasn't necessarily my idea, but I was the one that actually figured out how to make this neat little stuff. So this is what I did, all right? I went ahead and what you're looking at here, let me move this. I don't even know if you can see this. I'm going to move it. What you're looking at here are two graphs, right? So two separate graphs. So up top, you have the graph of sine x. And on the bottom, you have the graph of cosine x, right? So now remember, the derivative of sine x is cosine x. So that blue graph on the bottom represents the graph of the derivative of the top. Now, why would that make sense? Well, remember, the derivative, the outputs of the derivative, the y values on the derivative represent the slopes on the graph of f. So take a look here, right? This is the derivative. At this point, which happens to be pi over 2, but even if you didn't know that, at this point, what's the y value? The output or the y value is 0. We'll take a look. When you go over to the graph of x, f of x, which is sine x, you have a slope of 0, a horizontal tangent line. And now watch what happens as I trace this, right? That looks like a negative slope right there. Well, that looks like a negative y value. And since this is the slope producing machine, it would be y. All right, it would be a negative y. Now take a look at this. Oh, it's more negative. That's a steeper slope. Well, I have a more negative y value. And I keep doing this. And then like right around here, that looks like the steepest the slope's going to be. It actually occurs at an inflection point here. So that's where the steepest that slope is. So that's going to be the most negative. Well, look, the derivative is bottoming out there. And so now when I pass that point, right, I'm still negative, but not as negative. Well, there's my output y value, right? Then I come over here, still a negative slope, right? But not as negative. And I keep doing this, and then here, bam, back to where the derivative is 0. Well, there's the derivative being 0. Here I see it as the slope being 0. Here I see it as the output being 0. Now look at this part of the roller coaster. That slope is now what, guys? It's positive. So I don't know what this slope is, but let's pretend like for a second it's up 2 over 3. Take a wild guess at what that y value would be. Hopefully you're saying 2 over 3. right? Because the y values on the graph of the derivative represent the slopes of the tangents on the graph of f. And we can kind of see these relationships here. And I just kind of like doing this because that's kind of neat and fun. All right, so that's pretty cool. So sometimes they're going to ask you, hey, I want you to tell me, if I give you the graph of f, sketch the graph of the derivative. Well, a good spot to start would be, well, where are the slopes 0? Slope is 0 there, that's an x-intercept. Slope is 0 there, that's an x-intercept. What's happening in between? Well, they're negative, and it looks like there's a spot where it's most negative, so I'm going to have it bottom out, and that's how you can kind of get some rough sketches. There'll be more to come on sketching the graph of the derivative, but that's like a little introduction. And that also I wanted to show you because at first glance, you're like, the derivative of sine x, cosine x, that seems weird. But then when you see this, hopefully it's not as weird. All right, so let's get back at it. It says, note the proof for the derivative of cosine x, right, can be done in a similar manner. So if you wanted to show the derivative of this was negative sine x, it's very similar to this. The only difference is when you got to this part for cosine, you're using this expansion. And oh, by the way, look, there's a negative in there, so that might lead us to believe why there's a negative there. I'll leave that up to you. If you want to do that and submit that, maybe I'll throw you some points. All right. My next question is, how do you think we would start the proofs for these guys? Like, how would I go about proving the derivative of e to the x is e to the x and derivative of ln of x is 1 over x? Hopefully you're saying with the definition of the derivative. That's where you go with all of these. All right. So that part, the boring part, I say it wasn't boring. That's pretty exciting. So that part's over. Let's actually just do some practice. Let's go ahead and find the derivatives of each of these following functions. And we got to use rules that we know. So like when I go to do this one, you're like, oh, wait a minute. This is a constant times a function. So the derivative is just going to be the constant times the derivative of the function. And what is the derivative of e to the x? Well, it's the easiest one in America. It's e to the x, right? It doesn't always work like that, right? But with e to the x, it does. So this would be your slope producing machine for the graph of f. That one, pretty simple. You got to love e to the x. All right, what about this guy? Now, this guy's a little bit of a mess, right? Because you have like a product going on right here, and you have a quotient, and we don't know how to take the derivatives of those things yet, right? So you're like, well, what the heck can I do here? Hopefully you're thinking algebra. So I could, I'm going to kind of write it over here so I have some room. I could split this numerator up, write this as 2 radical x e to the x over radical x minus 5x over radical x, right? That's just splitting up the numerator. It's doing something very similar that I explained before. Now, why is it I'd want to do that? Well, because the radical x's here are going to cancel, cross those out, and they're going to be a 1. Now, this you might think is a little wackadoo, but you know what? I'll take my time here. I have 2e to the x, and I'm taking my time, and I'm going to rewrite this as 5x to the 1 over x to the half. And then maybe instead of writing 1, I write 2 over 2. And you're like, oh, okay. So when you divide two terms at the same base, you can subtract the exponents. So g of x is going to equal 2e to the x minus 5x to the, right? 2 over 2 minus 1 over 2 is 1 over 2. Or I could have just, wrote radical x there. All right. So now think about what we did, guys. None of this is in G prime. Do any of these say G prime? No, they don't, because we rewrote it first. Sometimes you're going to want to do that before you take a derivative. Rewrite the function to put it in a form that's easy for you to take the derivative of. So now when I go to find G prime of x, it should be easy breezy. All right, so here we go. Constant, all right, that's just 2, times the derivative of the function. Right? So constant times function, the derivative of that is just constant times the derivative of the function. Well, once again, the derivative of e to the x is just e to the x. That's easy. Now I have another constant times a function. So the derivative is going to be the constant times the derivative of this function. And the derivative of x to the half, if I'm doing the power rule, is 1/2 x subtract 1 subtract 2 over 2 to the negative 1/2. All right, and then I can just kind of spruce this up and say that g prime of x is going to be 2e to the x minus 5/2 x to the negative half. If I wanted to write that as 5 over 2 radical x, right, I could do that too. Half makes it the radical, the negative throws it in the denominator. All right, but that's it. That's your slope producing machine. All right, so let's take a look at C now. What's the deal there? So we have some sums and differences. Shouldn't be too bad, right? So h prime of x. Again, I have a constant times a function. The derivative of that is the constant times the derivative of the function. What is the derivative of sine x? Well, you now have that memorized. It's just cosine x. And yes, you're supposed to have that memorized. Minus constant times what's the derivative of e to the x? Easiest one in America, e to the x, right? Plus the derivative of 1, well, what's the derivative of 1? It's just 0. Derivative of constant is 0. So you're going to get h prime of x, when I clean this up, negative 2 cosine x minus 3 e to the x. There's my slow producing machine for the graph of h, okay? What about this guy? Maybe pause the video and try this one on your own. All right, when you come back, here we go. We can write y prime if we want, or maybe I'll go with this notation, which is always cool, dy dx. So here I go, constant times function. So once again, the derivative is the constant times the derivative of the function. What is the derivative of ln of x, right? The derivative of ln of x, you now have memorized, is 1 over x. Done deal. Minus, let's get my black pen out here. So minus the derivative of cosine x. So what is the derivative of cosine x? Well, that's the weird one. It begins with the C, right? The derivative of that is negative sine x. Notice I have to be careful with these negatives here. All right, and then you have the derivative of x cubed. Well, that's just a power rule, 3x squared. And now when I clean this up, maybe I have 5 over x plus sine x, right? And then plus 3x squared. All right, and there you have it. So what I like to do, I'm going to stop the video now. Go ahead and try these homework problems on your own, see how you do, but I will also post a video so that if you have trouble, you can walk yourself through.